Hi guys, this is the final review for Physics 2. We will be covering chapters from chapter 17 all the way up till chapter 26. I am starting off with chapter 17, which is wave optics, I believe. The very first question talks about Young's double slit experiment that I'm sure you guys have heard about in class. So the question says a double slit interference pattern is observed on a screen that is 2 meters behind two slits spaced 0.5 millimeters apart. Now from the center of one particular fringe to the ninth bright fringe is 1.6 centimeters. And we're going to have to find the wavelength of the light. So I know there's a lot of formulas, and if you look at the Study Union website, I have a study guide and this practice problem sheet. So if you refer to the study guide, there's a lot of formulas that I've listed based on the chapter. You can look at it, and there is a formula on there that says how to find the position for bright fringes in a double slit experiment. So what we're given is we're given D. The distance is 0.5 millimeters, right? And then we're given the length, which is 2 meters apart. And then the order of the fringe is 9. And Y is 1.6 centimeters. So we have to find the wavelength. Okay, so the formula for that is so this is the Y value on the screen, this is the order, and then that's lambda, that's the wavelength, and that is my distance from the slit to the screen, right? Okay. That being said, let's solve for L. So then that would turn out to be M no, we're solving for a wavelength, my bad. Missing something real quick. Give me 1 second, guys. Oh no. Actually, I'll just do this. Okay. So we have the formula right here. I kind of messed up on the formula, my bad. So this is the formula right here. When we solve for lambda, we have 1.6 centimeters that needs to be converted to meters. So that's going to be 1.6 times 10 to the negative 2, and then the distance would be 0.5 times 10 to the negative 3 meters. The order is 9, ninth order, so then that's why we have 9 here, and then the length is 2 meters. So if you do the math, you're going to get 400 nanometers. Any questions? Yeah, everything here is going to be recorded so you can go on YouTube, and if you miss anything, and I will also post this after the session too. It'd probably be after 10 a.m. tomorrow. But I should be posted by tomorrow. All right, let's move on to the next one. So we have a thin film of material with an index of refraction that says n equals 1.28, and is coated onto a plastic lens, and the refractive index for plastic lens is 1.55. It is desired to have destructive interference for wavelength 550 nanometers, so we're required to find the length of the film, or how thick is the film, not length, my bad, thickness of the film. So we have a formula that we use to find. So if you look at thin film interference in the study guide, there's a lot of formulas. One of them would be for destructive interference. And here, since we have two materials, so we have a thin film coated on top of a plastic lens. So our known is the refractive index of the film, the refractive index of the plastic lens, the refractive index of air, which is 1, and the wavelength is 550 nanometers. All right, our unknown is the thickness of the film. Oh, let me move it up. My bad. So I always draw a diagram. So this is the air layer. So then this part right here is the film. And then this is the lens. So since we know that the refractive index of film is higher or greater than refractive index of air, we're going to have a phase change, right? That's what that means when it's being reflected back. And then the same thing with film and lens. Since the refractive index of the lens is greater than the refractive index of film, we're also going to have another phase change, right? So there's two phase changes here. Therefore, if you look at, there's a table in the textbook, and if you look at it, it's going to have constructive and destructive interference with 0 or 2 phases or 1 phase. If it's being very confusing, just look at the study guide. I have uploaded on the Study Union website. All right, so we're going to use destructive interference for 2-phase change. The formula is thickness equals lambda over 2 times the refractive index. So in the table, it doesn't tell you what refractive index we're going to be using, either if it's film or the plastic lens. Since we're looking for the film thickness, we're going to be using the refractive index for film. Therefore, I wrote film there. All right, and then our order is going to be 0 because here there is no diffraction onto any fringe. We're not given there that the slit is, the path length of the slit is going on to the first bright fringe or the second bright fringe. So we're not concerned with the order at all. Therefore, the order is going to be 0. So if you plug everything in, it's going to be 550 nanometers at the wavelength over 2 times the refractive index of the film, and then times 0 as the order plus 1/2. And that gives us 107 nanometers. So here, notice how I didn't change or convert the units because we're looking for the wavelength, and every time you are asked for a wavelength, you're going to be looking for nanometers because that's the unit you use. So don't bother converting anything here because everything's given in nanometers. And the refractive index doesn't have a unit. So, all right. Moving on to the next one. Okay, so for this one, we have a laser beam that is aimed at a 1 centimeter thick sheet of glass at an angle of 30 degrees above glass. So we're looking for the laser's direction in glass, and then the laser's direction in the air, and then the laser's direction in the other side of the glass. So this is a classic example of Snell's law, where we're looking, when they say direction, they're actually asking for the angle. So let me write that down here. So direction means that you're looking for the angle. Now we know that Snell's law says that it's n1 times sine theta 1 equals n2 times sine theta 2, right? So here I have drawn another diagram that has, so this is air. This is air, this is glass, and this is air again. I mean, sheet of glass. Okay, so we have the angle of incidence right here, which is 60, because the angle of 30 is above the glass. So this has to be 30. This can't be 30. So every time we draw our angle of incidence, it has to be the one closer to the normal. So the dotted line, I don't know if you guys, yeah, that's the normal. So then theta, if we have to solve for theta 2, which is right on the other side. So it's on the glass right by the normal line. If you see, this is theta 2. That's what we're looking for, because we're looking for the laser's direction in glass. So we want to know the angle created by that laser beam in the glass, right? So then we solve for theta 2. You move everything on the side to isolate, onto the right side to isolate theta 2. So then that will give you arc sine of n1 times sine theta over n2, and then the whole thing is arc sine. So then you find the n1 is 1. So then that just gives us sine of 60 over 1.5. So if you plug that into your calculator, that should give you 35.3. So that's our theta 2 right here. Okay, for the second one, any questions so far? Yeah.
Is 1.5 just the index of glass?
Yeah. Yeah. Let me write that down. And then the n of the index of air is 1. Okay, so for the second one, we have n2 times sine of theta 3, which is this one right here. So this is going to refract onto an air again because it's moving into air, right? So notice how when we're going from air to glass, the angle, the theta 2, is kind of closer towards the normal. And that's what happens when you move from a lower refractive index to a higher refractive index. The angle of refraction moves closer towards the normal. And then if you look at glass and air right here, we're going from higher refractive index to lower refractive index, right? So notice how theta 4 is kind of moving away from the normal instead of going closer to the normal. That's a very important distinction to make because you might be tested on that. Okay, so then we have, if we put that in Snell's law, then we're going to have refractive index of the glass N2 times theta 3, because that's the one that's closer to the normal. Remember, we always pick the angle closer to the normal. Therefore, it's theta 3 equals N1 because we're going back to air. So we're using the refractive index of the air, and then we have sine theta 4, which is the refraction angle right here. Okay. So if we're looking for theta 4, we're going to isolate theta 4, of course, and then bring everything on the right side. So then it's the same thing as we did for the first one, except the angles are different. So this time we're using N2, which is the refractive index of glass. That means it's going to be 1.5 times the sine of the angle we just found, which is 35.3 over the refractive index of air. Yeah. That should be 2. My bad. Oh, I forgot to add this. Just kidding. So theta 2 equals theta 3, because they're on like, what are they called? I forgot. I'm like blanking out. Yeah, they're the same angle, but because they're not complementary, but I forgot. But we'll just go with that for now. I'll write that. I'll update that what it is. But it's like a geometry reason. I can't think of the term right now. Okay, so that's how we know that theta 3 is 35.3. So when we solve that, we're going to get theta 4 as 60. That's our last angle. So the laser's direction in the air, this is actually C because we're solving for theta 4. The laser's direction in the air would just be 30 degrees because that's when the laser hits the air and then it travels on the glass, right? So there's not really a problem. We're not solving here for anything. Okay. Any questions?
So you use Snell's law to find angle 2.
Mm-hmm.
Because of that, like the complementary angles or whatever the reason is, you
Mm-hmm.
say that angle 2 is equal to angle 3.
Yeah.
When you use angle 3 to find angle 4.
It's really not, yeah.
Okay.
So we're going to be using theta 3 because that's the one closer to the normal. That's why we're picking theta 3 and not theta 2. Does that make sense?
Yeah.
I can't think of the term. I know they're equal, but there's a specific geometry term that I can't think of. But I'll let you guys know after break if I take like a 5-10 minute break. All right. Any questions other than that? No? All right. So, this is, I think, from chapter 18. So, we're starting chapter 18 now, ray optics. A stamp collector uses a converging magnifying glass that sits, that sits 2 centimeters above the stamp, creating a virtual image. The magnification is 4. What is the focal length of the lens? So we're looking for focal length, which is f, right? Okay, quick review for the image. We have a virtual image, which means that it is an upright image, and that's going to have a positive magnification. So the magnification stays 4 for now. Because we have a virtual image, our image distance is going to be negative, right? Because a virtual image is behind the lens, not in front of the lens. So then we're going to be using negative S prime. So S prime is the image distance, right? And then S is object distance. Okay, so for converging lens, our object distance is going to be less than the focal length. That's what we know, and I think it's in the textbook too. So the magnification is going to be image distance over object distance. Therefore, if we solve for the image distance, it's going to be negative 4 times S because our magnification is 4. And that will bring us to negative 8 centimeters as our image distance, which makes sense because it's a virtual image, so our image distance has to be negative. As opposed to if it were to be a real image, your image would be inverted, right? And you would have negative magnification. All right. So if we use the thin lens equation to figure out the focal length, so the thin lens equation is 1 over focal length equals 1 over object distance plus 1 over image distance. So then we know that our object distance is 2 centimeters. So then that would be 1 over 2. And because our image distance is negative, so this is plus minus negative 8, which is going to be 1 over 2 minus 1 over 8. And that will bring us to 1 over 0.375, and that is 2.67, which is our focal length. So if you notice here, the focal length is actually greater than the object distance, which is what we wanted because it's a converging lens, so the object has to be inside the focal point. It has to be before. But the image that's going to be formed is behind the lens. Therefore, it's a virtual image. And a virtual image is always upright. Okay. Any questions? Let's move on. So this is a mirror, and a concave mirror has a focal length of 2.4 centimeters. Where should a candle be placed so that the image is inverted and is twice as large as the object? So right off the bat, we know that the image is inverted, which means that the image is real, and we're going to have a negative magnification. Well, how do we know what the magnification is? It's clearly not given directly in the question, but it says the image has to be twice as large as the object. And we know that magnification is nothing but a ratio of image distance to object distance, right? So we can tell that the magnification is going to be -2 right here. With a concave mirror, we're going to have a positive focal length, and our unknown here is the object distance, because we need to know where should the candle be placed. Therefore, what we're looking for is the object distance and not the image, because it's already given to us. Oh, just kidding, it's not given to us. We're given the focal length. But we can still calculate that because we have the thin lens equation. So in this problem, we're going to be using two equations, and we're going to be using magnification equation to substitute what we get for the image distance, and we're going to substitute that into our thin lens equation. So we're given the focal length again, we're given the magnification. It's -2 because inverted image, and inverted image is going to be on the same side of the mirror. It's real, therefore it's on the same side of the mirror, but it's inverted. Okay, so the magnification is, again, image distance over object distance. If we solve for the image distance, it's going to be negative magnification times the object distance. So we plug that into the thin lens equation right here. Because it's negative, we're going to just, well, I mean, it's negative, but the magnification is also negative. So I guess there's double negatives, which makes it a positive. So then that would be 1 over s plus 1 over 2s. And if you do the math and find the common denominator, we're going to have 3 over 2s. So that's 3/2 s. Okay, so 1 over focal length equals 3 over 2s, right? Which is, this is the object distance, and this is our focal length. Let me write that down. Which is essentially what we're looking for. So if we cross multiply, we're going to have 3f equals 2s. If we solve for s, we're going to have 3f over 2 equals 3/2 times 2.4 centimeters, which is our focal length, and that gives us 3.6 centimeters as our object distance. So the distance of the object from the mirror is 3.6 centimeters. Therefore, the candle should be placed 3.6 centimeters in front of the mirror. So it's going to look something like this. Right, that's a concave mirror. Oh, you can't see it. So then our object should be somewhere right here, 3.6 centimeters from the mirror. That's what that means. Okay. You can also calculate the image distance. I don't have it on here as a part of the question, but if you want to go ahead and solve that, you can. The only difference that would be you would be solving for the image distance. So then that would just be negative, what is the object distance? 3.6. So it would be -2 times 3.6 centimeters. I mean, this would be positive because the magnification is -2. So then that would be 7.2 centimeters, I believe. So our image distance is 7.2 centimeters. All right, any questions? Okay, let's move on. Am I going too fast? All right. Okay, so we're moving on to chapter 20, I believe. So chapter 19 is not part of the curriculum for any professor as far as I know. Therefore, chapter 20 is electric field and charges. So we have two positive charges spaced at 3.7 centimeters apart. We're looking for the net force on the one positive charge that is in between those two charges. So obviously we're going to be using Coulomb's law, which states that, which helps us find the force that one charge exerts on another, because we know that charges exert force on each other. We use Coulomb's law to calculate what the force is that one exerts on another, and vice versa. So in this case, we have three charges, and here is a diagram. So this is my Q1, 10 nanocoulombs. Q2 is 20 nanocoulombs. And then the one in between is Q3, which is 0.5 nanocoulombs. All right, so the distance between the first and the second charge is 3 centimeters. Because we know that the third one is placed exactly midway between them, it's 1.5 centimeters for the distance between Q1 and Q3, and then 1.5 for the distance between Q2 and Q3. And for the force, we know that so we represent force as a vector quantity too. So the force direction for the force that charge 1 exerts on charge 3 is going to be in the right direction, so it's going to be in this direction, and then the opposite direction for the force that charge 2 exerts on charge 3. Okay, that being said, let's dive right into the formulas and let's solve this. So our known is obviously the 3 charges and then the distance between them. We're looking for the net force. When we are asked to calculate net force, we don't subtract anything, but we add. So we're going to be adding force. To calculate the net force, we're going to be adding force of charge 1 on charge 3, and then we're going to be also adding force that is exerted from charge 2 onto charge 3. Okay, so for the first one, F1 on 3, the formula for Coulomb's law is the electric constant times the 2 charges, and don't forget that the charges are in absolute values. You will be given the equations or the formulas depending on the professor you have, but I would suggest if you don't, you should write this down because it's an important formula. All right, moving forward, the electric constant is 8.99 or 9.0 depending on your professor again, times 10 to the 9 Newton times meter squared over Coulomb squared. I recommend you guys write the units because they're very important, and that will help you cancel all the units and make sure that you have them in the right order. Okay, so then for the charges, the first charge is 10 nanocoulombs. Q1 is 10 nanocoulombs, and it has to be in absolute values, so that's going to be absolute value, times Q3, which is 0.5 nanocoulombs, which is going to be 0.5 times 10 to the negative 9 coulombs, again absolute value, over 1.5 times 10 to the negative 2 meters squared, because it's centimeters and we want our distance to be in meters. So this is actually meters. I just made it worse. Oh. All right. So that gives you 2.0 times 10 to the negative 4 newtons. And then if we were to calculate the force that charge 2 exerts on charge 3, we would use the same formula, but we would just change the charges because this time it's between charge Q2 and Q3 over the distance. So if we plug in the numbers, it's going to be the electric constant times Q2, which is 20 nanocoulombs, so 20 times 10 to the negative 9, I was going to say 19, no, 10 to the negative 9 coulombs, and the absolute value of that, and then 0.5 nanocoulombs, so that'd be 0.5 times 10 to the negative 9 coulombs, over 1.5 times 10 to the negative 2 meters squared, because it's the same distance, right? All right, and that gives us 4.0 times 10 to the negative 4 newtons. So now we have to add this and this. So if we add that, we're going to get 6 times 10 to the negative 4 newtons, and that's our net force. Net force of that charges Q1 and Q2 exert on Q3. Any questions? Yeah.
Wouldn't one of these charges be negative, like Q2? Because since they're both positive,
Mm-hmm.
and the middle one is positive, wouldn't the middle one be going towards the left?
Are you saying Q3 goes on to, so in the direction of Q1?
Yeah.
For F1 on 3?
No, I'm just asking in general, because wouldn't Q3 start heading towards the left, since it has a greater charge going against it in Q2?
Oh, I see what you're saying.
I just don't think they'd add up. I think one of them is negative, but I'm not 100% sure.
The textbook said that they don't really have, so I know that what you're thinking is in terms of magnitude, that 0.5 is definitely smaller than 10, therefore 10 should be the one exerting, like it should be pulling towards itself. I see what you were saying, but we're plotting the direction of the force that one exerts on another according to the question, not if we didn't have the question that asked for the forces on charge 3 specifically, it would look a little different, but since we're only focused on how the two charges affect the third one, we're not so concerned with like the magnitude. We're only like plotting the direction of force, so to speak. Does that make sense or no? Sort of. So just think of it as, so we're only plotting the vector quantities because we want to see, okay, what direction or what charge is exerting force on which charge. So in this case, we want to know what the force is that is exerted on charge 3 by charge 1, right? That's why we have the direction, the rightward direction, because we're looking for the force that is exerted by charge 1 on charge 3. So if it were to be towards the left, that would mean that we're looking for the force exerted by charge 3 on charge 1. Does that make sense? Yeah, so we're just plotting what the question's asking for. We're not like actually going into and like making a detailed explanation of what the charges mean in terms of magnitude. Is that good? Okay. Any other questions? Okay, let's move on. Oh, if I were to have a quick variation right here, so let's say if I were to change the 20 nanocoulomb to negative 20, then it would look a little different, because now that we have a negative charge, we're going to have more pull towards the negative charge, right? Because negative charge attracts. So if I were to draw real quick, if I were to draw the electric field lines for a positive charge versus a negative charge, it would look something like, so positive has field lines directing away, right? Each of these are away. And then for negative charge, we have the field lines that are pulling it towards. So every time you have a positive charge, it's going to go away from itself, basically. And it's going to look for a negative charge to go towards itself. Okay. So moving on to the next question, that's it. It's asking for the electric field. So we're looking for the strength and the direction of electric field that is 2 millimeters away. So the distance between the electric field and proton and an electron is 2 millimeters. So we're going to consider the electric field of a proton separately and then electric field of an electron separately. So they're two different individual problems. The strength we can calculate with the electric field formula, but the direction is a little different. So what this line means basically is that if the charge is less than 0, so we know that the charge of an electron is 1.6 times 10 to the negative 19 coulombs, but it has a negative connotation to it. And then for proton, our charge is 1.6 times 10 to the negative 19 coulombs. So, because my charge is less than 0, my electric field for electron would be coming towards the electron. So the direction would be towards the electron. And then for proton, since it's greater than 0, so it's 1.6, definitely greater than 0. And so then that means that the proton's electric field is moving away from the proton. All right, so let's dive into the math part. We have the distance from the charge to the electric field, which is 2 millimeters, and we also know the charges. Okay. The unknown is the electric field of electron and proton. Direction, we already covered that. Okay. So this is the electric field formula that has the electrostatic constant and times the absolute value of charge over the distance squared. Okay, so electric field is measured it's measured in newtons over coulombs. Charge has the unit of coulombs, and this is meters squared. And this is just electrostatic constant that we already know what it is. Okay, so let's do the electric field of a proton. That would just be plugging in things. So then 8.99 times 10 to the 9 Newton times meters squared over coulomb squared times the absolute value of the charge of a proton, which is 1.6 times 10 to the negative 19 coulombs, over the distance, which is 2 times 10 to the negative 3 meters. This is important because we know that 1 centimeter equals 1 meter is equals 100 centimeters, and then 1 centimeter equals 10 millimeters. So then that's 10 to the negative 3, right, if we go from 1 millimeter to meters. So be aware of the conversion factors because they will give you something that is not meters, and you will be required to convert them into meters to get the right answer. That being said, if you do the math, it's going to be 3.6 times 10 to the negative 4. And for electrons, it's going to be the same as well because it's an absolute value of charges. So the only difference we're looking for basically is the direction of electric field, which is going to be a little different, but the electric field is going to be the same because we have the absolute value for the charges, so it doesn't make any difference. And their answer is 3.6 times to the negative 4 Newton over coulombs. Okay. Moving on to the next one. Okay, so this one right here is an example of, I think it's chapter 21. So the proton is moving through an electric potential that is created by a number of source charges. Its speed is 3.0 times 10 to the 5 meters per second at a point where the potential is 1200 volts. What will be the proton's speed at a short time later when it reaches a point where the potential is negative 200 volts? This is a question that uses law of conservation of energy. That means that we have the final kinetic energy plus the electric potential. The final electric potential energy equals the initial plus the initial electric potential energy, right? This one is a big problem, and I already worked it out. So since we're running out of time and we have a lot more to cover, I'm gonna post this online, but just know that since the proton is moving from high potential to low potential, we know that our electric potential has to be less than 0. Therefore, if you see right here, the way I arranged the final and the initial voltage is Vi minus Vf. Therefore, we know that the initial is smaller than the final. Therefore, we're going to have a negative change in electric potential, right? So be mindful of that right here. And then I also wrote if the proton were to move from low to high potential, then you would have the electric potential greater than 0. So then basically it's just plugging in and solving for the final velocity, because we're looking for the proton speed after a short time when the potential is negative 200. So that's our final potential. And so if you plug everything in, that should give you 5.9 times 10 to the 5. All right, let's move on to the next one. All right, this is another example of point charges. So we have a point P, and it's just talking about how far it is from these two charges, and we're supposed to find the net electric potential of both the charges. So the formula for electric potential is this, which is electrostatic constant times charge 1 over R1. So everything's given to you. You're given the distance, and if you plug everything in, then you will get 225 volts. The only thing, another important thing is that since I already mentioned this in the calculating net force section, it's the same thing that's whenever you asked for calculating net potential or like net force, net potential, you're not going to be subtracting anything but adding. So we're adding two things to find the net potential of both the charges. Because it's a point charge, we're looking for the potential that both of these charges have on point P. So I also wrote down the table that you can look at for, because it shows the difference between point charges and the charge inside an enclosed space. So I'm not sure if your professor went over the enclosed space, but if they did, then you can go over and look at that table, and that has everything you need to know. Okay, moving on. So we have a capacitor and a battery, and we're looking for the charge on the capacitor. So we're going to be using this formula right here. Q stands for the charge, C is the capacitance, and this is the voltage of the capacitor. So we're given the capacitance, we're given the voltage, we only have to find the charge on the capacitor. So 1 millifarads is 1 times 10 to the negative 3 farads, and then the voltage is 1.5. So if we were to calculate for the charge, we use this formula and we plug everything in. Since it's a capacitor, we know we're going to have a positive electrode and a negative electrode. So it only asks for what's the charge on the capacitor. It never asked for a particular electrode. So I went ahead and put the charge on the positive and the charge on the negative. It stays the same because they're technically protons and electrons, and we know that protons and electrons have the same charge, just different opposite signs. So yeah, pretty easy. All right, moving on to the next one. This one in particular is related to resistivity, and the formula for resistivity is right here, where R stands for resistance, the rho is what the resistivity is, L is the length of the wire, and A is the cross-sectional area of the wire. So we have a 20 centimeter long, so that's our length. Our diameter is 0.4 millimeters, which means the radius is going to be 0.2 millimeters, and then that's going to be 2 times 10 to the negative 4 meters squared, because it's r squared. And then the voltage is 1.5, right? So the wire is made up of nichrome, and the resistivity for that is 1.5 times 10 to the negative 6 ohms times meters. So if we plug everything in, since we're looking for the current, we have another step that we have to go further down to find the current, because here we're looking for the resistance, because we don't have the resistance of the wire. We're given everything else. So if we solve for that, we're going to get 2.39 ohms, and then we plug that into the V equals IR formula, Ohm's law, right? And that's going to be, if we solve for I, it's going to be voltage over resistance. So voltage is 1.5 volts over resistance 2.39, and that gives us 0.63 amps. So our current that's running in the wire is 0.63 amps. Are we good?
Can you explain where you multiply the voltage 1.5 times 10 to the negative 6? Explain why.
1.5. Oh, right here?
Yes.
Because that's the resistivity, so that's the formula. If you see right here, it's resistivity times length. So resistivity of the wire, which will be given to you, is 1.5 times 10 to the negative 6 times the length, which is 0.2 meters. Because it's given in centimeters, but you convert that into meters. And then the radius is in millimeters, so you convert that into meters. And then you have pi, because the cross-sectional area of a wire is going to be pi r squared. So then you divide that by pi r squared, and then you get the resistance. We good? Okay. Okay, so this one is just another example of how you would calculate resistance if you were to be given power, voltage, and current. So the formula that we have for power is, this is the main generic formula, but if you were to, because we're looking for resistance, right? Resistance is in this formula. So there's another way that you can kind of maneuver the formula to have resistance in it. One that has the current and resistance is this one, and the other one is V squared over R. So you can use either of these formula because you're given the voltage and the current. It's just plugging into the formula because everything is in the right units. Therefore, just plug it in, and you should be getting 240 ohms as your answer. Okay. Next one. Oh, this is a... Okay. This is a big one. So, we have to find the total resistance, the total current, and the current and voltage drops through each of these resistors, right? It's not that bad, just stay with me. Just don't lose it. Okay, so the very first thing that you would want to do is to condense the circuit, right? So I would go ahead and attack this one right here. The very first part would be to find the resistance equivalence of these two parallel resistors. So then because they're in parallel, we know that we're going to be using the resistance equivalence formula for resistors connected in parallel, which is 1 over 3 plus 1 over 6, right? Because R2 is 3, R3 is 6, and that will give us 1 over 2, but since this is to the negative 1 power, it's going to be 2 ohms. So that's the first one. So if you were to condense this circuit, it would be 2 ohms right here. So that turns out to be 2 ohms. And then if I further condense this, because now that all the resistors are connected in series, it's going to be, I'm just going to add everything now. So it's going to be 2 plus 2 plus 4, right? So that's when the resistors are connected in series. So you would calculate the resistance equivalence according to this series. formula, and that would give you 2 plus 2 plus 4, and that's 8 ohms. All right, so now we're given, so we found the total resistance. This is the total resistance in the whole circuit, right? Because I have the total resistance and the total voltage, which is 24 volts right here, I can find the total current, which is 3 amps. Because we know that from Ohm's law, V equals IR. And if we isolate I, we're going to get V over R, and then that gives us 3 amps. Okay, so we have to go back and find the current and voltage going through every single resistor. That's the hard part. So we know that the resistors connected in series are going to have the same current passing through them, right? Because, and this is important, I recommend you guys write this down in your notes somewhere, that resistors in series have same current passing through them, but different voltage. And then parallel is different current that passes through them because it's a junction, right? Parallel circuits, parallel resistors are connected or like are separated by junctions. So the current kind of divides between those two, therefore it's not the same current, but we do have the same voltage passing through each resistor connected in parallel. Okay. That being said, we know the current passing through resistors 1 and 4 is going to be 3 amps, which is the same as a total current because there's no drop in here. Okay, so if we were to calculate the currents in these two resistors, we're going to have to find the voltage first, right? So for that, for the voltage for series, because it's going to be different, so we have to calculate this first. Therefore, it's going to be V equals IR. You just use the formula, and the voltage for resistor 1 would be 6 volts because it's the current times resistance, right? So it's 3 times 2, and that gives you 6 volts. And then for the voltage in resistor 4, we're going to have I4 times R4, which is going to be 12 volts. So if you add these two together, that's the voltage drop overall in series. And if you subtract that, so that's 18 voltage drop, right? And then you have to subtract the 18 volt from the total, which is 24. So 24 minus 18 is 6. Now this is what we have. This is the remainder of the volts that passes through the resistors connected in parallel. So each of these has 6 volts passing through them, right? If we go back to calculating the current passing through these two, now that we have everything, so we have the resistance and we also have the voltage, we're just going to use the Ohm's law, and that would be 6 over 3, that would give you 2 amps, and then for the third resistor, it would be voltage is 6 divided by the resistance, which is 6, so 6 over 6 is 1, right? And that's how you have all of these right here. Are we good? Okay. So I feel like that was a lot. And this is something I have for practice. You guys can practice it. I will post this online tomorrow, sometime tomorrow. So I'm not going to go over that one. And then this is just the another version of circuits, but we have capacitors instead. So with capacitors, I'm just going to write what you usually do with capacitors, how you would calculate the capacitance equivalence. So capacitance equivalence in series and in parallel. So remember how in series for resistors, we just add them all together? It's different in capacitors. We would do 1 over, so it would be 1 over that equals 1 over C1 plus 1 over C2 plus however many you have to the negative 1. So it's the reverse of, so you know how we calculate the resistance in parallel? That's how we would calculate capacitance in series. So then for parallel, it's pretty easy, right? We would just add them all together. That's it. So then if you use this formula and use the same technique that we used earlier in the problem, you should be able to get to the final, or the total capacitance, which is right here. 11.37 microfarads. And again, I will post this so you can check your answers, but we're not going to go over this for the sake of the time. All right, how about we take a 5-minute break? Oh, did you pause? Okay, let's start with the capacitor problem. This talks about, so remember how we had time constant and exponential decay with the current? So what that essentially means is the voltage or the current that's being created in the circuit is gonna decay over time, because as the capacitor is being discharged of the charge, as time passes, we're gonna have less and less of the current in the circuit from the initial point, which is t equals 0 when the switch is turned on, right? So this one in particular has a capacitor and a resistor, and it's connected to a 9 volts battery. Now we're looking for the current in this circuit immediately after the switch is closed, so that's t equals 0. That just means that we're looking for the initial current, right? And the second part of the question states what the current is 25 microseconds into the circuit. Okay, so our initial voltage is 9 volts, right? Because that's what we're going to start off with, and that's how much the EMF is. So when the switch is closed, our initial current is going to be initial voltage of the capacitor over resistance, which is 9 volts over 10 ohms, right? And that gives us the initial current, which is 0.9 amps. So that's the current as soon as the circuit has the switch closed, right? So as soon as the switch is closed, the current is going to be 0.9 amps. Okay. With time, though, we use a different formula for that, and it's in the textbook and the study guide, again, that I uploaded. Okay, so we have to find the time constant before we dive right into the current formula. So the time constant is R times C, which is resistance times capacitance. And that's just one of the other formulas that you need to use for exponential decay of voltage and current. All right, so this is the Greek letter tau, and it represents time constant. So our resistance is 10 ohms. Our capacitance is 1 microfarads, which is 1 times 10 to the negative 6. So then this is how many seconds I have, and if I were to calculate that or convert that into microseconds, because so there's 2 ways you can really do this problem from here. You can either keep it this way and convert the 25 microseconds into just seconds, so that would be 25 times 10 to the negative 6. Or you can convert this into microseconds, and that way you're in the same unit. Either way, just make sure that your units are similar so you can cancel them. Okay, so then that gives us 10 microseconds right here. And if I were to calculate the current, this is the formula for the final current, which is initial current times e to the negative t over tau. So this is the time that we're asked for, and tau is the time constant, right? So 0.9 amps times e to the negative 25 microseconds over 10 microseconds, which is going to give us 0.074 amps. And that's the current in the circuit after 25 microseconds. So our initial current is 0.9 amps, and then our current after, or at 25 microseconds, exactly, would be 0.074 amps, which makes sense because we're starting off with 0.9 amps, and as time passes by, it's decreasing, right? Any questions? All right. For this one, I pulled this problem out of your textbook. It's just asking for a circuit diagram based on what we're given here. So we have a 6 volts battery. I'm not sure if the picture is clear enough, but so this is a 6 volts battery, and it's connected to 2 parallel resistors. And here it's connected to a series resistor, which is connected to another resistor in series, which is connected to a capacitor, ultimately connected to the bulb. And the bulb is connected to the two parallel resistors as well. So if we were to put that into a circuit diagram, this is what it would look like. Just make sure that when you are drawing the parallel circuits, they have to be sharing a junction, right? Like, I mean, they divide into a junction, but it has to be dividing from like the same wire of the circuit into another one, and then right back up, and then continuing on to the circuit. This? No, it's a light bulb. An inductor would look something like this. Yeah. I know it looks like a light bulb. I just realized. I mean, inductor. I just realized that too. No, but it's a bulb. Right? It's a bulb. It's not an inductor. Doesn't look like. Yeah. Okay. Just making sure. Okay. On to the next one. Okay, so we have a solenoid model, and its length is 1 meter and the diameter of 1 meter as well. The field inside is 4 Teslas, so right away we know that this is something with magnetic field. And we're looking for the turns of wire the solenoid has to have in order for it to produce a field of 4 Teslas. And we're also given another condition that the current in the wire is 150 amps. With all of that, how many turns should the wire have, or the solenoid model have? Okay, so we're given the magnetic field. So B is magnetic field is measured in Teslas. Length is 1 meters. What is this? Oh. No, that is not correct. This is, just kidding. Okay, I should probably just change that. Okay, so the magnetic field is 4 Teslas. The current is 150 amps. And the N is for the number of turns, right? N stands for the number of turns. Okay. So this is the formula that we would use to calculate the magnetic field in a current carrying wire. Since we have a solenoid and we're concerned with how many turns, I added N here. But if you were to calculate magnetic field in a current carrying wire without any turns, just a normal current carrying wire, it would be B equals the constant times current over L. Okay, so if we solve for the number of turns, it's the length times field over the constant times current. And that will give us 1 meters times 4 Teslas over 1.26 times 10 to the negative 6 Teslas times meters over amps. And then the current is 150 amps. So with the math, it's 21,164 turns. I should put a comma there. There we go. Okay. Any questions? Okay. All right, here we go. So this question is asking for the direction of the magnetic force on a positive charge. So right away we know that we're going to be using the right-hand rule. And for us to use the right-hand rule, we have to have a proper understanding of where exactly is the velocity of the charge or the current of the charge is. So I recommend you guys draw a diagram. So here's mine. This is my wire, and the current is moving towards the right, yes? So then if you use the right-hand rule, the first one so we're going to be using two right-hand rule basically. I'm going to tell you that right away. The first right-hand rule is going to give us the direction of the magnetic field. Once we have the direction of magnetic field, we're going to be using the second right-hand rule to calculate the direction of the force, right? So since my current is going towards the right, I don't know if I can do it right here, but let's say if this is the direction, and let's say if I were to hold the wire, it's going to be, I'm going to curl my finger like this, right? So it's going into the plane from this side, and it's coming back out from the other side, right? So then that makes sense that we have, so dots is out of the plane, crosses into the plane. So then we're going into the plane and coming right back up the wire.
I think you're fine, but this was like supposed to be done by 9:30. Do you know like how long? Yeah, you guys are gonna be here for
10:30.
10:30. All right, I'll just let somebody know.
Okay. Okay, what was I talking? Yeah, so we have the direction of magnetic field. So this is magnetic field, right? So then if we use a second right-hand rule where we use our thumb as the direction of current, our index finger is magnetic field, and the other one is force, right? So I don't know if I can do that on here, but I don't know if I'm flicking at someone. Can I come here? Is it going to be? It's not going to happen anyway. It doesn't matter. Okay, I'll just do it here. Okay, so our current is in this direction, and then our magnetic field is pointing right out at you, right? So it's going to be like this. So then the magnetic force is going to be coming right towards the wire, right? So it's facing downwards. Does that make sense? No, we have to find the magnetic force, right? So we have to use the second one. Does that make sense? Okay. So I know I put down the magnetic field direction in both the sides of the wire, but we're essentially focused on to the top part, right? Because that's where our proton is. So orient yourself onto the top part of the wire, like above the wire, not below. So on top of the wire, if I wrap it up, it's going to come out of the plane, right? It's coming towards me. So that means that my magnetic field is going to be pointing right at me, right? So then the force has to be in the direction towards the wire. So the force has to be downwards. Cool? Question? Yeah. So if the charge were to be somewhere here, then it would be different, right? Okay, so that was a proton, right? And if we have positive charge, we don't change the direction of the force. But if we were to be given a negative charge, then we use the right-hand rule the same way we would if we were to be given a positive charge, but we just change the direction, or we flip the direction of magnetic force, right? So if this were to be an electron, you would change the direction. So instead of facing downwards, it would be upwards. Yes? Cool. Oh, there's already another one. Okay, so I have another problem right here, and it talks about electron. For the sake of time, we're not going to go over that. But the answer for that one is the magnetic force is going to be pointing out of the page. Yeah. Okay, let's go to the next one. Okay, so this one has, why do I have an Earth? Oh yeah, okay. So we know the sun is emitting charged particles moving towards the Earth, and I think it's a proton. I forgot to add it, but the proton is moving towards the Earth at a speed of 500 kilometers per second. And that's the speed, right? At this point, the Earth's field is 5 times 10 to the negative 5 Teslas directed parallel to the Earth's surface. What are the direction and magnitude of the force on the proton? So we're also going to be using the right-hand rule here, along with calculating the magnitude. But to calculate, we're going to do the magnitude first. So to calculate that, we have the velocity, which is 5 times 10 to the negative 5 meters per second. Because we're given kilometers, we don't need that. We need to convert that into meters. So we know that 1 kilometer equals 1,000 meters. That's what that's for. So if you do the math, that's 3 plus 2, 5. Magnetic field is 5 times 10 to the negative 5 Teslas. It's already given in Tesla, so we don't need to convert it. And so here we know that the magnetic field is moving parallel to the Earth's surface, right? So if the Earth's surface is this way, it's going to move parallel. The magnetic field is moving parallel to the surface. But the velocity of the particle is approaching towards the Earth. So let's say if this were to be my particle, its magnetic field is pointed in the upward direction, right? But the charge is moving towards the Earth. Therefore, we have we know that the magnetic field and velocity are perpendicular to each other, right? So then that's going to be 90 degrees. That's how we know the alpha is 90. Okay. So then if we use the magnetic force formula, F stands for magnetic force. Let me write that. Okay. The formula states that we have the absolute value of charge times velocity times the magnetic field, right? We also have sine of alpha, but since it's already 90, we don't have to worry about that. Cosine 90. Okay, so the charge of a proton, since we know that's a proton, it's going to be 1.6 times 10 to the negative 19 coulombs times the velocity, which is 5 times 10 to the 5 meters per second, times the magnetic field. And that gives us 4.0 times 10 to the negative 18 newtons. So if we were to use the right-hand rule to calculate or to figure out the direction of the magnetic force on the proton, it would be something like, so it would be going into the page. Right? Because the magnetic field is moving upwards, so it's moving upwards, right, like this. So this is current, and this is magnetic field. And then if I just use the other finger to calculate the force, it tells me that it's going to be into the page. I don't want to Does that make sense? Okay. Okay, so let's do another one with magnetic flux. So we have Earth's magnetic field, 50 microteslas, tipped at an angle of 60 degrees below the horizontal. There's a 10 centimeter diameter circular loop of wire that sits flat on the table. What is the magnetic flux through the loop? Okay. So I recommend you draw the diagram first, since we have angles and it could get confusing. So for the flux, there's a diagram in my study guide that I made that has this image of magnetic flux. It's also in the textbook if you look at it to see which angle in specific we're looking at when we have magnetic flux. So the the angle that this is talking about is right below the horizontal. So that means that that's the one that's interacting with the magnetic field and the horizontal line of the wire. But we don't need that. We need the electric field, the angle between the magnetic field, sorry, the normal between, no, we need to, sorry, we need to look at the angle that is between the magnetic field and the normal line, which is 30, right? Because we're given, let me draw it again. So let's say this is the wire, and it's coming at this angle. So we're given this angle. This is 60. But what we need to look for with the formula, the angle in the formula is asking for is the angle between the normal line and the magnetic field lines. So then it would be 30, right? Because this right here makes a right angle. So since this is 60, this has to be 30. So this is the angle that we're going to be using in the formula and not 60. All right, that being said, if we convert the magnetic field into Teslas, it would be 50 times 10 to the negative 6 Teslas, and the angle is 30. The distance is 0.05 meters because the diameter is 10 centimeters, so 10 divided by 2 is 5 centimeters, or 0.05 meters, right? The formula for magnetic flux is magnetic field times the area times the cosine of the angle between the magnetic field and the normal. Okay. Since the area of the wire is probably going to be a cross-sectional area as well, so then we're going to have to use pi r squared. So our radius is 0.05 meters, therefore that's 0.05 meters squared. Okay, and that gives us 3.4 times 10 to the negative 7 Webers. So magnetic flux is measured in Webers. This is Webers. Weber. Any question?
So for these problems, every time it says the angle is below the horizon, you have to take the complement of it?
Yes.
For, I know this is like going back, but like for the index of refraction, is like one of the first problems. So for that too, if it says the like angle is above the glass, you take the complement for that too, right? The one where it was like going through the glass and the air.
So for that one, you have to look at the angle. So in terms of the formula, you're only going to be using the angle that's closer to the normal.
Oh, right, yeah.
So make sure it's always going to be the one that is closer to the normal for Snell's law. Yeah.
Okay.
Any other questions? All right. Okay, so this one's a bit long, but this question uses Lenz's law. Which basically states that if you have a change in magnetic flux, there's going to be an induced magnetic field that's going to oppose the change in that flux, right? So with that induced magnetic field, we also have an induced current, because we know that magnetic field induces current and current induces magnetic field. So we use the direction of the induced magnetic field to calculate the direction of the current, or the induced current. Okay. So the first one states to find the direction of induced current if the magnet moves towards the coil. So I drew a diagram. It's not the best, but it gets the job done. Okay. So for A, the magnet is moving closer, or it's moving towards the coil, right? That means that it's going to have an increasing change in flux, right? Not a change in flux, increasing magnetic flux. Okay, so to oppose that change, we're going to have an opposite induced magnetic field, right? So that's the induced magnetic field direction of the lines, sorry. Since they're in the opposite direction, if we use the right-hand rule, you would find that the current is moving in the clockwise direction. So if we use the right-hand rule, it's going down, so that means that the current has to go this way. So since it's a loop, I recommend you roll your, or you curl your fingers into the loop, like towards the loop, right? So since it's going in the loop, your hands are just gonna go down, right? In, like, let's say this is the loop, then it's gonna go in. So then the direction your thumb faces is towards the left, so it's gonna go like this, right? That's why it's clockwise. Okay. The second one states to find the direction if the magnet is moving away from the coil. For this one, if the magnet is moving away from the coil, we have this scenario right here. So it's moving away, therefore we have a decreasing magnetic flux, right? So think about it as, don't let the field lines confuse you. This just means this is the field lines produced by the magnet. Since it's going away from it, we have a lesser and lesser magnetic field in here, right? So to oppose that change, we're gonna have the induced magnetic field lines go into the coil instead of opposing that change as well. So with that being said, if you use right-hand rule, if you curl your fingers into the coil, it's gonna be something like this, right? So this is the coil, and then your finger or your thumb is gonna face towards the right. So then that gives us the counterclockwise direction of the current. So the current moves in counterclockwise direction. Any questions? All right, for the last point, if the magnet remains stationary, then we have no induced current. So C will have no induced current because we only have induced current when we have an induced magnetic field, and we have an induced magnetic field when we have a change in flux, right? Because nothing's moving, everything's stationary, we don't have a change in flux, right? Therefore, none of that occurs. Yeah. Yeah. In this case, you really don't have to curl up because we're not looking for the direction of magnetic field. So just know that we're going into the coil. So let's say if this is a coil, I'm just going to face on my fingers right there. So then it's going to face in the left direction. Okay. Okay. So this is chapter 26, I believe. No, it's still 25, just kidding. Yeah, it is chapter 25. So this question is in specific with the photon energy, and we know that light there's 3 different theories to the way light acts, right? So light could be in terms of wave, or light could also act as a ray or particle, and light can also act as a photon, right? So this is from chapter 25, where we were talking about how light acts as a photon, and if we were to calculate the photon energy of the light, we would go ahead and use this formula. So E stands for the photon energy, and H is Planck's constant, F is obviously the frequency. Okay. Since the question states that what is the photon energy in electron volts for the germicidal lamps that use wavelength of 254 nanometers? We're given the wavelength. We're not given the frequency. Well, there is a way that we can substitute frequency in terms of the speed of light in vacuum over wavelength, right? Because we know that this formula can be used that gives us the speed of light in terms of wavelength and the frequency. So if we substitute frequency, we're going to get speed of light over the wavelength. Okay, so we just plug that in here. This is Planck's constant times speed of light over wavelength. So then we get 6.63 times 10 to the negative 34 joules times second. That's our Planck's constant times the speed of light, which is 3 times 10 to the 8. I'm not sure if your professor is going to give you this because it is a constant. Yeah, because it's speed of light in vacuum. We already know what it is, right? I would recommend if your professor doesn't give you that, then have it somewhere in your notes because you're probably going to use that. And then you divide that over the wavelength, which is 254 nanometers. And here is where we're going to change our units, right? We're going to convert nanometers to meters because we need to cancel the velocity or the speed because the speed is in meters over second. If we put in nanometers, we can't cancel it, and then we have a wrong answer. Okay, so that would be 254 times 10 to the negative 9 meters. Therefore, you have 7.83 times 10 to the negative 19 joules. And let me do this one again, because let's say if we have 7.83 times 10 to the negative 19 joules. And if they would ask you the energy in terms of electron volts, they'll probably give you the conversion factor. So the conversion factor for electron volts is 1 joule. 1 electron volts equals 1.6 times 10 to the negative 19 joules. And that will give you 4.89 electron volts. It's just simple dimensional analysis, right? Coming in handy. Okay. Any questions? All right. Okay. So this is chapter 26. So chapter 26 is about alternating current. A little bit about alternating current is that there is oscillation of current and voltage, right? With direct current, we have no oscillations. It's just the direct current or direct voltage that we get. And it doesn't change over time. I mean, it does if we want to, but it stays the same for the most part. But with current and voltage, we have oscillation, which means that we have peak currents and peak voltages, and we have instantaneous current and instantaneous voltages. So for peak currents, we have we use a notation called I, and then for peak voltage, we use capital V, right? So those are the peak current and peak voltage. And then for instantaneous current and instantaneous voltage, we use small letters. So this is instantaneous. So since we have oscillations of current and voltage, be mindful that we could have a positive and negative value of, so we're going to have a positive peak current and a negative peak current. And if you're confused at what I'm talking about, then I recommend you go back to the textbook or the PowerPoints. It should have a graph that has oscillations between the current and voltage, and a very nice table towards the end that has all the, I think it's an RLC circuit that has all the graphs that talks about how with inductor we have, I don't know if I'm right on this, but I think it's current lagging the voltage, and then with the capacitance it's the other way around. I recommend you look at the table, it helps a lot. Again, that table is in the study guide if you want to look at it. So let's do this problem. We have a hot wire that dissipates 680 volts when plugged into a 120 volt outlet. And that makes sense because 120 volts is what we use for all the outlets in America, and those are all 120 volts. So then that means that we have alternating current. So we have AC circuits all over. Wherever you see an outlet, that's alternating current, basically. Okay, so we're looking for the wire's resistance. For this one in particular, we have power and we have voltage, and we're looking for resistance. So if we look at the formula for power, for direct current, it looks a little different, right? So for power, we have, and I went over this earlier too, but I'm just going to write that down again. So it looks something like this. The only difference between this and the one in AC current is you just add RMS. That just means the root mean square value of the voltage, and then when you have, where you have I, you're going to do the same thing. So that's what that means. And then this is the power of a resistor. Okay, so that's what I have right here. The power of a resistor equals V RMS squared over R right here, just the same version, we just changed a little bit. Okay, so if we isolate resistance, it's gonna look something like this, right? And that will give us 120 volts over 580 watts, and that will be 25 ohms. So 25 ohms is our resistance, and we're gonna be using that for the next part. Any questions up till now? Okay. So the second part, we're going to be using this part right here of the formula, which is right here, right? So since it's squared, we have to take a square root in order for us to figure out the current at RMS. So it would be the square root of 580 watts. Why did I put 580? It's 680. Oopsie. Sorry guys, this is 680. Okay, so it would be 680 watts over 25 ohms, and then you take a square root of that, which would give, probably this is not the right answer. It would be something else. Can anyone do the math for me real quick? No calculators? Yeah. Oh, I thought you said first one. First one.
First one is 21.
Okay, perfect. And then, so this would be 20. So what's the second one? Perfect. And then can you do 5.7 times square root of 2? Sorry.
It's 8.047.
Okay, that looks right. So once we have our current in root mean squared, the IRMS, we use that in order for us to because we also have to calculate the peak current, right? So we use the RMS and the relationship between RMS and the peak current to figure out the value of peak current, basically. And this is given in your textbook, the formula. So this is an important formula. And this one is. All right, any questions? Okay. So I have this question, and I figured it's a little too complicated. Oh, this one right here. So I'm not gonna go over it, and I mean, I will post the solution to this online, but I feel like it's way too complicated, and I don't think it's gonna be on any of the exams. So, yeah, just by looking at it, it's like you don't even want to do this problem. Yeah, that's all I have for you guys. Any questions? Any concept questions? Let me see if we can go over anything. All right, well, since we have time, let's do this one. Something I skipped earlier. Okay, so number 20 asks for the direction of magnetic force when we're given the direction of magnetic field and electron, right? So when you draw the diagram, it should look something like this, where you have your magnetic field pointing upwards and then your electron is facing towards left. So if we do the right-hand rule on this, it's going to initially point into the page, right? But that would be the answer if you were to be asked for an electron. Yes? Proton. Proton, sorry. That's magnetic field. Okay. Yeah. So the velocity is towards the left, and so it should look something like this, right? So the magnetic field or the force is pointing into the page, but it's an electron, so it's going to point out of the page, right? Cool. Then we already did that one. Was it this one, Danielle? Right here?
Yes.
Okay. I know it's a little, let me draw it a little bigger so it's easier to comprehend. So this is air. Okay, so this is air, this is glass, and this is air. Okay. So this is n equals 1, n equals 1.5, and the refractive index of this is 1. So we know that the light hits this at a 30-degree angle. So I draw my normal right away. And then we always look for the angle that is towards the normal, attached to the normal, right? So since this is 30, this is going to be 60. And that's the angle essentially what we're looking for. Now, it's going to be refracted, but it's going to be closer to the normal, right? So this is my theta 2. All right. And here's another normal that I would draw right away. And this is my theta 3, right? Okay, so since we're going from a higher refractive index to a lower refractive index, we're gonna go away from the normal. So that is my theta 4. Does that make sense?
Right, so I guess what I want to know is there any case where they would give us the angle that's already closer to the normal, or would it say that? Or would it say the angle of refraction when the laser meets the glass is this, then you already have it?
So here it says angle is 30 degrees above the glass. That's how you know that it's going to be the one closer to the glass.
Right.
Because this line right here is glass surface, right? Technically. Okay, so if they were to give you that it strikes the the glass, and the angle of incidence is 30, or like it hits the glass surface at 30, then you would use.
60.
No, you wouldn't use 60.
Oh, if you're saying if it strikes closer to the normal on 30, use 30?
Yeah. It should tell you though.
The wording for some reason on these types of problems just trips me up.
I know, and that's why I put
You
it
need to
there.
draw a picture and then I'll be good.
Yeah, I feel like that's the best way to go for these problems. So, okay, so for this one, I can't think of the term, but if you guys can like kind of see that these two are like parallel lines, are they called parallel angles? Do you guys remember from geometry? Like they're the same, right? Like they're the opposite sides. So like then this, no, I can't do that. But if it were to be like this line right here, then this angle would be equal to this angle. Do you know what I mean? I can't think of the term. Oh, it's like making me guys. Yeah, I don't know what the term is, but that's what it is. So parallel angles, that's why they're equal. That's why I did theta 2 equals theta 3 right here. Yep. And then for the second part of Snell's law, we're going to be using theta 3 and theta 4, right? Okay. All right, that's it. Any other questions? No concept questions either? Okay.